Assalamu alaikum. In this video, we study how to find extreme values of some function with constraints. That means if we want to find some extreme values of this function f of x and y, with which is subject to some constraint, say g of xy equal to 0. So that means x and y must satisfy this relationship with each other. And with this constraint, we want to maximize or minimize this function f of xy. So how do we do that? One convenient way to do this is to use the method of Lagrange multipliers. It's better to explain this using an example. So consider finding extreme values of this function x squared plus xy plus y squared with the constraint x plus y squared is equal to 0. So this is the constraint here. So that means we want to maximize or minimize this function where x and y moves on the unit circle centered at the origin. So x squared plus y squared equal to 1 means x and y are on this unit circle. So the radius is 1 and the center is at the origin. So while x and y moves on this circle, what is the maximum or minimum values of this function? That's the question. Actually, this problem is not so difficult to solve because we can explicitly solve this equation for, say, y. So y can be expressed in terms of x. Then we can substitute that y into this equation, here and here. Then we have a univariate function of x. Then we can maximize or minimize or find any extreme values of this function. But here we use a different approach, that is to use the method of Lagrange multiplier. So first, we define this function g of x and y, that is x squared plus y squared minus 1. So we just moved this one to the left. And then the constraint can be expressed as g of x and y equal to 0. So this is equivalent to this constraint, right? So with this constraint, we want to find the extreme values of the function f of x and y. To do so, we first define another function by combining these two functions in this way, in the following manner. So capital Y, f of x and y is equal to f of x and y minus lambda g of x and y. So we define this new function where this lambda is undetermined multiplier. It's a constant or a variable. So this is called Lagrange multiplier. Lagrange multiplier. Okay, sometimes we call it Lagrange undetermined multiplier. Well, whatever. Then if this constraint is satisfied, this term will vanish. So maximizing or minimizing lowercase f of x and y is equivalent to maximizing or minimizing the uppercase f of x and y. I will just show how we use this method before explaining how it works, okay, or why it works. First of all, we have just defined this function and we differentiate it with respect to x. Okay, so f of x is this, and g of x and y is this. So let's write the function f explicitly here. So that is x squared plus xy plus y squared minus lambda x squared y squared minus 1. And we differentiate it with respect to x. Then we have 2x plus y minus 2 lambda x, and differentiate it with respect to y, and we have x 2y minus 2 lambda y, and we also differentiate with respect to lambda, xy. So lambda is only here, so we have negative x squared plus y squared minus 1. Okay, so we pretend to find the extreme values of this function. Okay, so since there are three variables, x and y and lambda, we differentiate this. So if this function takes an extreme value, then all these derivatives should be equal to 0. Okay, let's solve these. Let's label this as 1, 2, 3. First, let us simplify these equations. So from 1, let's factorize this. We have 2, 1 minus lambda x plus y equal to 0. From 2, we have x plus 2, 1 minus lambda y equal to 0. And 3, we have x squared plus y squared equals to 1. Okay, so from the first equation, let's put y equal to, let's see, 2 lambda minus yx. Substitute this into the second equation. We have x plus 2, this 2 lambda minus y x equal to 0. Okay, so we have x here, so factorize them. We have 1. Let's flip the sign here. We have 2 1 minus lambda and 2 1 minus lambda. Okay, so we have 2. Let's put a lambda minus 1. Squared. Okay, so this is 1 is of course 1 squared, so it's squared minus squared. So we have the following: 2 lambda minus 1 and 1 plus 2 lambda minus 1. So we have, let's see, 1, 2, that's 3 minus 2 lambda, and this is 2 lambda minus 1. So we have x equal to 0, or lambda equals to 3 over 2, or lambda equals to 1 over 2. So if, however, this possibility is excluded, because if x is equal to 0, then okay, from this one, then from 1, y must be equal to 0, right? So if we substitute x equal to 0, then y is equal to 0, whatever the value of lambda is. And but this contradicts with equation 3, this one. But x equal to y equal to 0 contradicts 3, because 0 squared plus 0 squared is not equal to 1, right? So this cannot be satisfied. Therefore, x is not equal to 0. So we have only two possibilities here. Lambda equals to 3 over 2 or 1 over 2. Okay, so let's consider these two cases. If lambda is equal to 1/2, from this equation, we have y equals to 2 lambda minus 1x equals to 2, 1 over 2 minus 1x, so that is negative x. And so y must be negative x, and from the condition 3, that is x squared plus y squared plus equal to 1. So if we substitute y equal to negative x, then we have 2x squared is equal to 1. So therefore we have x is positive or negative 1 over square root of 2. And therefore x and y are plus minus 1 over square root of 2 and minus plus 1 over square root of 2. So these signs should match, okay? Positive, negative, negative, positive. Okay. And next case, for lambda equal to 3 over 2. Again, we use this equation, and y is equal to 2 lambda minus 1x. So 2, 3 over 2 minus 1x. So that is x. Okay. Again, from the constraint, we have x squared plus y squared is equal to 2. And if y is equal to x, we have 2x squared is equal to 1, and x is plus minus 1 over square root of 2, and which is equal to y. Therefore, we have x and y equal to plus minus 1 over square root of 2 and plus minus 1 over square root of 2. So this plus corresponds to this plus, and this minus corresponds to this minus. So if we visualize these points on the unit circle, so these points are indeed on the unit circle centered at the origin. So these are these 4 points. Okay, plus, so this is positive 1 over square root of 2 and positive 1 over square root of 2. And also negative. So that is negative this and negative 1 over square root of 2. So these 4 points are the extreme value points. Okay, we still don't know whether they are local maximum or local minimum. Now, you should note that the gradients of the tangent lines at these points are not infinity. So at any of these points, the tangent has slopes that are not infinity. So this satisfies the condition of the implicit function theorem. So there exists an implicit function say phi of x of g of xy equal to 0. Okay. So using this implicit function, we can express the original function to be maximized or minimized as this. So f of xy becomes f of x and phi of x. Now this is a univariate function of x. So let us define this function as h of x. Okay. Now finding the extreme value of f of x and y became the problem of finding the extreme value of h of x. Next, consider the constraint g of xy equal to 0. So if we substitute the implicit function here, we have g of x phi of x equal to 0. And in this case, it's x squared plus phi of x squared equal to 1. So if we differentiate with respect to x, so differentiate with respect to x, we have 2x plus 2 phi of x using the chain rule, we have this. So we don't actually know the exact functional form of phi of x, but we do know from this relationship the derivative of phi is given by this equation, that is x over phi of x. Okay, we will use this relation later. Now, our problem is to find the extreme values of this function. Okay, so we first differentiate h with respect to x. So that is, so we use the multivariate version of the chain rule. So first we differentiate f with respect to x and differentiate x with respect to x, right? That is one. And we differentiate f with respect to y, that is the second variable, and differentiate phi with respect to x. So that is fx. And this is 1. And fy. And this is phi prime. Okay. And from the definition of f of xy, that is this one. Okay, so if we differentiate with respect to x, we have 2x plus y. And if we differentiate this with respect to y, we have what is it? X plus 2y. And phi prime we just obtained as this. So that is negative x over phi of x. And of course, y is actually phi of x. So that's phi of x, and this one is also phi of x. So let's simplify a little bit. What do we have here? So that is, let's see. It's phi of x here, and 2x plus phi of x plus x plus 2 phi x. This is minus. And let's see, 2x phi plus phi squared minus x squared minus 2x phi. So this will cancel this. And phi squared minus x squared and phi of x. And we want to simplify a little bit more. Since x squared plus phi squared is equal to 1, we can get rid of this phi squared. So that is 1 minus x squared, so that is 1 minus 2x squared over phi of x. And of course, this is equal to 0 at extreme points. And they are indeed 0 because as we have already calculated, x and y are, where is it? Either 1 over square root of 2 or 1 over square root of 2. So if we substitute these values, we only need actually x, and 1 over square root of 2 plus minus, this is equal to 0, right? So if you just substitute 1 over 2, so square root of 2 squared, so this is 1 and it's 0. So this becomes 0 at those points we have just identified. Now, to decide whether these points are maximum or minimum, we need to differentiate this function again. So let's do it. So h double prime is equal to, so differentiate this one. Using the quotient rule, we have negative 4x times phi. Just we skip this parenthesis x and minus 2x squared phi prime over phi squared. Now, we again get rid of this phi prime using the relationship we have obtained here, this one. So that's 4x phi minus 1 over 2x squared minus x over phi. Let's multiply both numerator and denominator by phi. We have 4x phi squared 1 minus 2x squared x plus phi cubed. Okay, so what do we have here? Okay, let's see. We have negative 2x cubed, negative 4 phi squared x plus x. Okay, let's factorize this x. Here. Okay, now we had x and phi of x as plus minus 1 over square root of 2 and plus minus 1 over square root of 2. So if this is the case, then what happens? Then h double prime of x is, so this is negative 2 and okay, let's say we take the positive part, okay, positive 1 over square root of 2 and positive 1 over square root of 2. In that case, we have this and 1 minus 4. So that is, if we square it, we have 1 over 2 and 1 over square root of 2. And if we take, so phi of phi cubed is 1 over square root of 2 cubed. Okay, so what is it? Negative 1 over square root of 2 and that is 2, so negative 1 and this is 2. So what is it? Negative 2 and 2, 2. So we have negative 4. That is negative. Okay, so the second derivative being negative means this is a local, what is it, maximum or minimum? It's maximum. Okay, so this is the case for positive 1 over square root of 2 and positive 1 over square root of 2. But if you do the same thing for negative square root of 2 and negative 1 over square root of 2, then you still get the same result. That is negative 4. So for these points, by the way, this corresponds to, which one was it? Okay, 1 over 2 corresponds to, okay, so this corresponds to lambda equal to 3 over 2. Okay, and if x and phi of x are plus minus 1 over square root of 2 and minus plus 1 over square root of 2, then what's the value of h double prime? So if you do the same thing, so let's take the positive x and negative y. Okay, then we have negative 2 cubed, and that's negative, okay, this, and over, that is negative. So this is equal to positive 4, I think. Yeah, it should be positive 4. That is positive. So this corresponds to local minimum. So let's summarize. So we have x, y equal to plus minus 1 over square root of 2, plus minus 1 over square root of 2. And they are, so if xy, what, by the way, what's the value of f of x and y at this point? That is x squared plus xy plus y squared is, let's see, so they have the same signs. That's 1 over 2, 1 over 2, 1 over 2. That's 3 over 2 is the local maximum value. And at xy equals to plus minus square root of 2 and minus plus 1 over square root of 2. So if you do the same calculation, that's 1 over 2, negative 1 over 2 and 1 over 2. So fxy is 1 over 2 is the local minimum value. And we are done. Okay, you should notice that in this solution, we never needed to find the explicit form of the implicit function phi, right? So phi remained implicit all the way. Actually, in this particular problem, we can actually solve, we can actually find the explicit form of phi that is actually so. For example, if this, since this is the constraint, we can solve this for this. Y is equal to plus minus square root of 1 minus x squared. So either positive or negative square root of 1 minus x squared is an implicit function. But we never needed this form in this, so if we use the method of Lagrange multiplier. So that's the beauty of it. So in this case, we are lucky enough to be able to solve for y, but in many cases, this is not possible. So we cannot find explicit form of the implicit function. So, but still, we can apply this method. Now let us provide the theoretical basis of the method of Lagrange multipliers. So let us give this theorem. Lagrange multiplier. Okay, let f of xy and g of xy be of class C1. So that is at least once continuously differentiable. Okay, so both of these are. Okay, and with a new variable, lambda, that is real, we define capital F of x, y, and lambda that is equal to f of x, y minus lambda g of x, y. Now, at the point AB, suppose the following conditions hold. That is, first, the function f of x, y has an extreme value. At AB, subject to constraint, the constraint g of xy equal to 0. So that is g of, so since this is satisfied at this point, that means g of a and b is equal to 0. Okay, and 2, the point AB is a regular point. Point of g of xy equal to 0. Okay, recall that this equation defines a curve in two-dimensional space. And a regular point of a two-dimensional curve means that the partial derivatives, one of the partial derivatives is non-zero. So that is the partial derivative with respect to x, AB, is non-zero, or gy AB is non-zero. Okay, it is not the case that both of these are 0. Okay, one of these can be 0, but the other must be non-zero. Okay, now suppose these two conditions are satisfied, then there exists some alpha, a real, that satisfies such that fx a b alpha equals to fy a b alpha equals to f lambda a b alpha equal to 0. So this is just like a necessary condition for the extreme value of unconstrained functions. But for the constrained problem, then we define extended function, and this function, so the maximization or extreme value finding of this function with constraint can be considered as unconstrained extreme value problem of this extended function. Okay, so let's prove this theorem. First of all, from the first condition, from this condition, we have this, right? So from the first condition, condition 1, we have g of AB is equal to 0. So f lambda of AB alpha is equal to, so if you differentiate this function with respect to lambda, what we have is just negative g of AB, which is trivially 0 because we're assuming this condition. So therefore this is trivial, and it suffices to show show that there exists alpha such that f of x a b alpha is equal to f xy, wait a minute, it's ab, minus alpha gx ab equal to 0, and fy ab alpha fy ab alpha gy ab equal to 0. So all we need to do is to find such alpha that satisfies these two equations. And next, by condition 2. Condition 2, we have either this or this. Okay, and without loss of generality, we may assume that this is the case. Okay, without losing generality means we may assume either this or this, but if this doesn't hold, then we can just switch the roles of x and y, and we can always assume this is the case. Okay, and still the same argument applies. So without losing generality, we may assume gy ab is non-zero. Okay, then by the implicit function theorem, there exists an implicit function f of x such that g of x and phi of x is equal to 0. So if we use this implicit function, then the problem of finding the extreme value of f of x and y becomes f of x and phi of x. Okay, so we need to find the extreme values of this function. Okay, now from here, but before that we have from this, if we differentiate this with respect to x, then we have gx and 1. So dx, just for the sake of completeness, just write everything down. Okay, so we are using the multivariate chain rule here, and gy phi x and d phi dx equal to 0. So we differentiate both sides of this equation. So this is of course 1, so we can just erase that. And this is phi prime, right? Phi prime of x. Therefore, we are assuming this is non-zero, okay? So therefore we can divide by it. Phi prime of x is negative gx phi x over gy x. To do this, we needed to assume that this is the case. Okay, now let's differentiate f with respect to x. Maybe we should write this as h of x, okay? Since it's a univariate function. So if we differentiate it, applying the multivariate chain rule, we have fx and dx plus fy x phi of x and phi prime, right? And now phi prime is this one. So substitute it. Negative gx gy. And if AB is an extreme value point, then if we substitute A and B here, this should be equal to 0. So let's substitute it. Fxab equal to minus Fyab and Gxab and Gyab equals to 0. And now let's look at this equation. We have fx here and gx here. So move this one to here. We have this Fyab over Gyab times Gxab equal to 0. Now, let this thing be equal to alpha. Then this alpha clearly satisfies the first of these equations, right? So this alpha is Fy over Gy. So this is satisfied. And what about the second one? That's trivially satisfied actually. So if alpha is this, then Fyab minus alpha Gyab. So just substitute this alpha. And Fyab and Gyab and Gyab. So this is cancelled. Then this is cancelled. So this is 0. So we have the desired alpha. And we are done. By the way, we assume that Gy is non-zero. But what if it was 0? Then we just do the same thing using Gx. Okay, so instead of Gy here, so implicit function will be x equal to some function of y. Okay, so it's not function of x, but it will be function of y. And we can do the same argument to find a very similar result. And that's it. See you later.